In this video, we're going to learn how to find the area between two curves. Let's first remember how we find the area under one curve. So if you'll remember, using the first fundamental theorem of calculus, the integral, or the area under the curve, of f of x from a to b is big F of b minus big F of a, or this area minus this area, which gets us the area in the middle. Maybe we could do something similar to find the area between two curves. Now imagine you're trying to find the area of this region, the shape between f of x and g of x. So like how we did when we found the area under one curve, we're going to take two areas and subtract them. So how I'm going to begin is I'm going to call this intersection point A, and I'm going to call this intersection point B. The first area we're going to take is the integral from a to b of f of x, because this integral gives me the area from here all the way down to the x-axis. So all of this stuff. And then I'm going to go ahead and subtract the area under g of x from a to b, or all of this stuff, like so. So what we're doing here again is we're taking this big area and subtracting this bottom area from it to get this remaining region. And because of the properties of integrals, we can write this as the integral from a to b of f of x minus g of x dx, or the integral of the top curve minus the bottom curve dx. One small modification to the formula: if you have a scenario like this where we're still trying to take the area between the two curves from a to b, but they have a third intersection here in the middle, we're going to call this point C, then we have to reflect that in our integral, because it's always top curve minus bottom curve. But here, the top curve changes depending on which region we're in. So in this case, the area between the curves from A to B is the integral from A to C of f of x minus g of x plus the integral from C to B of g of x minus f of x dx. Like that. Because from A to C, f of x is the top curve, so we have top curve minus bottom curve, but from C to B, g of x is the top curve, so we have to reflect that, so we have top curve minus bottom curve. And that's how you find the area between two curves. I'm going to do two examples for you. This first one says, find the area enclosed between x squared and square root of x. It's always nice when you're doing these kind of problems to have a picture so you know how many intersection points you have to find. For reference, in the first quadrant, this is what x squared looks like, and this is what root x looks like. So we have to find these two intersection points. So what we do is we simply set them equal and solve. I'm going to square both sides. Then I'm going to subtract x like this. And you don't want to divide by x to get x cubed equals 1, because then you miss out on a solution. From here, I'm going to factor out an x, like so. And from here, you can easily see x equals 0 and x equals plus 1. So now we found our intersection points. Now we're going to set up our integral. So we have the integral from our intersection points from 0 to 1 of, so if you remember, the top curve was actually square root of x, minus the bottom curve, which is x squared, dx. And now it's just a manner of doing the integral. We have, this is 2/3 x to the 3 halves minus 1/3 x cubed, evaluated from 0 to 1, which is, we have 2/3 minus 1/3 minus 0 minus 0, which is 0, so we can just get rid of this. And so this is 1/3. And that's the area enclosed between x squared and square root of x. And for the second example, we're going to find the area between 2 sine x and tangent x between negative pi over 2 and pi over 2. The reason for this domain restriction is because both sine and tangent are periodic or repeating functions. Just so you guys have a picture of this as we're working, so this curve is 2 sine of x, and then this curve is tangent x. We can clearly see that we have to find 1, 2, and 3 intersection points. So I'm going to begin by letting 2 sine of x equal tangent x, like so. And then I'm going to simplify tangent x into sine over cosine, like here. And then I'm going to multiply both sides by cosine of x, like here. And now I'm not going to divide by sine x because then we'd miss out on a solution. Instead, I'm going to subtract a sine x from both sides, like so. And now I'm going to factor out a sine x from the left, like so. And now it's clear that we have to solve two expressions to find our intersection. First one is sine x equals 0, and the second one is 2 cosine x minus 1 equals 0. I'll start with this. So we're asked the sine of what angle is 0. In our unit circle, you know that's x equals 0 and x equals n pi. Since n pi is outside the domain we've set here, I'm going to disregard this solution. Here we just have x equals 0 for this, and you can see that's this intersection point. We're going to find these two using the second expression. I'm going to add 1 to both sides, and then I'm going to divide both sides by 2, like so. And now we have to find the cosine of what angle gives 1/2. Again, from the unit circle, we know that this is x equals plus or minus pi over 3 and x equals plus or minus 2 pi over 3, like so. But this plus minus 2 pi over 3 is outside the domain we set here, so I'm going to disregard this solution. And now we found our three intersection points: negative pi over 3, 0, and positive pi over 3. So now we're going to set up our integral. And notice that we have to split into two integrals because the top curve changes at x equals 0. So our integral is the integral from negative pi over 3 to 0 of, so the top curve here is tangent x, minus the bottom curve, which is 2 sine of x, like so. From here, we're going to add this area, which is the integral from 0 to positive pi over 3 of top curve, which is now 2 sine of x, minus bottom curve, which is tangent x, dx. So this is the whole expression for the area between the two curves. And now we just have to solve the integral. So I have the integral of tangent is negative ln of cosine of x minus the integral of sine is negative cosine. So actually this should be a plus. All of this evaluated from negative pi over 3 to 0. Plus, and then we have the reverse order here, like this. Now we just have to evaluate the definite integral bounds. And I'm going to do just this one first. So we have like this. And evaluating this, this is, so cosine of 0 is 1, and ln of 1 is 0. So this is 0, and plus 2 times 1, here's 2, minus, so the cosine of negative pi over 3 is positive 1/2. So we're going to leave it as negative ln of 1/2 plus, so cosine of negative pi over 3 is 1/2, so this is 1. And when we evaluate this, we get this is, because this becomes a positive, and then this becomes a minus 1, which turns this into a 1. Now we're going to evaluate that part. This is the second part all written out here. Now if you go term by term, so cosine of pi over 3 is 1/2, and negative 2 times 1/2 is negative 1, plus the ln of 1/2, and then minus, so the cosine of 0 is 1, and so negative 2 times 1 is negative 2, plus the ln of 1 is 0, so this is just negative 2. Evaluating this, this becomes 1 plus ln of 1/2. So with both parts evaluated, we can now simplify this. which, if you really wanted to, you could rewrite as 2 plus the ln of 1/4 because of the ln property. And this is the area between 2 sine x and tangent x in the interval -pi/2 to pi/2.